5, Day 3, Relations and Functions. As a refresher, we have this warm-up problem that it actually turns into a linear regression problem. So the scatter plot shows the monthly high temperatures for Austin, Texas, in degrees Fahrenheit over a 12-month period. Scatter plot. Which function best models the data from month 1 to month 9? Now I want you to pause the video and see what you can come up with for this. And here in just a second I will go over it. No, seriously, pause it. Okay, so what you would want to do is actually month 1 to month 9. So we're actually ignoring, grab a different color. We're ignoring the data that's over here. So between here and here. And which of these functions actually could come from that? Month 1 to month 9. So what I would do is actually create a table of the data. So 1, and these are actually going by 2, so that's 90, 2 and 99, 398, 499, etc. Put those into your calculator. Now, if you remember, it's menu, statistics, it was all from the scratch pad. Menu, statistics, stat calculations, statistics calculations, linear regression with mx plus b. Linear regression with mx plus b is our answer. So once you put your data, make sure you put this in a list. Your x lists, your x's, and your y's. What you should come up with is an equation that is y equals 2.5, I'm not going to round this, 2.53x, or I'm going to round it to 2 decimal places. 2.53x plus 90.55, which is closest to h. Another thing we could do to actually reduce our choices is draw a trend line. That has a positive slope because these points are tending to increase. So we shouldn't have a negative right here, and we could automatically eliminate those and choose between those two. But it is, in fact, h. Okay, so on our notes, one of the big ideas is we're going to be able to identify functions, and the other big thing is we're going to identify the independent and dependent variables in situations, and writing a depend statement. So I'm going to actually write a depend statement for all of these, even though it doesn't say to. We have an iPod. Let's see if I can move this. There we go. So an iPod's available memory and the number of songs that have been downloaded. So I feel like I could say something like available memory depends on the number of songs downloaded. The available memory depends on the number of songs that are downloaded. Okay, so what we could say for that then is that the available memory is the dependent variable. So the dependent is the available memory. Okay, and the independent is the number of songs. So there we have it. The dependent is the available memory, and the independent variable is the number of songs, because the dependent always depends on, hence the words, depends on the independent. So here, the time spent studying and a student's algebra grade. Let's see if we can say this one out loud. The student's algebra grade depends on the number of time spent studying, the amount of that. So that means that the grade is our dependent. Grade is our dependent variable. I'm going to abbreviate that. Our independent variable is the time spent studying. Okay. Number 3, the time spent brushing your teeth and the number of cavities. I think it would naturally make sense to say that the number of cavities depends on the time you spend brushing your teeth, because the more you brush your teeth, the fewer cavities you're going to have. So our dependent variable is the number of cavities. While the independent is the time. Time brushing. By the way, a really common thing is that your independent variable will be time. It's not always the case, but it sure helps. Number 4, the number of candy bars bought and the change from a $10 bill. So I would say that the change that you got depends on the number of candy bars you bought. So our dependent is our change, and our independent is number of candy bars. Okay. So if you can say that out loud, one depends on the other, then you are almost there. Now, it's a really common thing that time is independent. It's also a very common thing that money is dependent. Money depends on other stuff. So that's just something to keep in mind. Now, tell whether y is a function of x, and then explain. Well, number 5 is not a function. It's not a function because the definition of a function is going to be that every x has one y. Okay, so function. Every x, and I should say it this way, every x has exactly one y value. So the question is, do you have any x's here that have more than one y value? Well, 1 is matched up with 4, but then it's also down here matched up with 7. It's written differently, but 1 is matched up with both of those. So it fails that. So we're going to say 1 has 2 y values. Number 6, 2 is matched up with one thing, 1's matched up with one thing, 0's as well, -1 and -2. So this one is a function because every x has exactly one y. Every x is exactly one y. Okay, now in number 7, we can look at this and we can actually, these arrows mean that 8 is matched up with -3, 8 is also matched up with -4, and it's also matched up with -9, so no, because 8 has 3 y values. But I should also point out that 9 also has more than one y value. 9 is matched up with 2 different numbers. Therefore, you could actually say either of those reasons, but the point is that there is an x, there's an x that has more than one y. Number 8, make a table, graph, and mapping of this set. I'm going to start out with writing these here. So our x's, -4 matches with 0, -2 matches up with 2, and 0 matches up with 4. Looking at that, we can tell if it's a function or not, because our x's should have only one y. So if our x's repeat, that's a bad thing. They do not repeat, so it is yes. Every x has exactly one y. Now, if we are to plot these, we would get -4, 0. Let me grab a different color. -4, 0. -2 and up 2. 0, 4. Okay, now on our mapping diagram, we will always write our x's and our y's in this way. It's going to look just like our table. -4, -2, 0, 0, 2, 4, and those match up. -4, -2, and 0. Number 9, make a table, graph, mapping of the set. So again, I'm going to write these points. We have 3 matches up with 5, 2 matches up with 4, 3 matches up with 3, and if you notice, we've written 3 twice in this one column, and 0, 4. So really, I should point this out. What really matters is the x's when it comes to is it a function or not. These 4s repeating, that's actually okay. It's not a function if the x's repeat. So it is not a function because 3 has 2 y values. All right, so if I plot these, we have 3, to the right 3 and up 5, to the right 2 and up 4, to the right 3 and up 3, 0, 4. Okay, and there's also another way we can tell if this is a function based on looking at it. So 3, 2, we've already written 3, and 0. So we're going to go and write these over here. We have 5, 4, 3, and we've already written 4, so I'm only going to write it once there. So 3 matches up with 5, and you'll see what I mean in a second. 2 matches up with 4, 3 matches up with 3, and 0 matches up with 4. So what we are actually looking for is if we have an x value that has 2 of these arrows coming out of it. They break the rules. If one of the x's is shooting in 2 different directions, that is a problem. I had a teacher when I was actually in college. We talked about functions, and his favorite thing to talk about was Lord of the Rings and that type of thing. And so he imagined these two being 2 armies. And the rules here are that the people in the first army have 1 arrow, and exactly 1 arrow, hence the function. And they can shoot their arrow one place. So it's okay right here if 2 and 0 both are shooting at the same guy, they're double teaming him. That's okay. That doesn't break any rules. However, 3 showing up with 2 arrows, where did he get the arrow? He broke the rules. So that's just something that helps to keep that in mind. Now, something we're going to see in a second, I believe. I'm going to point it out now. That if you notice, if you look at the graph here, you can see that one of these x's, that 3, is going 2 different places because they're sitting on top of each other. You don't want that to happen. Okay, and then it'll actually come back to be called the vertical line test. Okay, let's look at number 10. Make a table, graph, and mapping. By the way, this is called a mapping right here. 2, 0, 1, 4, -1, 3, and -2, 4. None of the x's repeat. This is a function. Every x has exactly 1 y value. Plotting this, we get 2, 0, 1, 4, -1, 3, and -2, 4. Nothing sits on top of each other. That's good. X and y, we've got, we have +2 first, 1, -1, -2. And our y value is 0, 4, 3, and we already wrote 4. So 2 goes to 0, 1 goes to 4, -1 goes to 3, but -2 goes up here 4. Everybody has 1 arrow. That's good. Okay, now the vertical line test. What it comes down to is, so the vertical line test. Okay. If you can cross a graph more than once with a vertical line, it is not a function. If you can cross a graph with more than once, with a vertical line more than once, it is not a function. See if I can explain that a little bit better. When you look at 11, okay, none of the x's go more than one place. We don't have any vertical stacking. That means our x's have 1 y that matches up with them. So the way that you can do this, though, is if you take a vertical line, like I'm doing, and you try to cross over this. Take it over the graph. Is it ever going to hit more than once? No, it is not. So our graph is a function. because every x has exactly one y. Okay, number 12, I guess I could have used the same one. Number 12, if you try to cross this, actually anywhere, let's just say like right at 2. Oops. At 2, right there, this x goes 2 different places. This x right here has 2 y values. There's vertical stacking. That is not good. So this one is not a function. Okay, and I'm going to say that 2 has 2 y values. There are lots of places this fails, but it definitely doesn't work at 2. Okay, number 13, take my vertical line. It's ever going to cross more than once. I'm not seeing it. I made it without a problem. So this one is a function because every x has exactly one y. Three more like this. We will take a vertical line. Where could you cross 14 with a vertical line more than once? How about right there, right on top of that? So this one is not a function because it looks like 3 has more than one y value. More than one y value. Doesn't matter how many it has, as long as it has more than one. Okay, number 15. Hey, look, you can't ever cross that more than once. It only hits once. So this one is a function. Every x has exactly one y. Looks like I can cross actually right here. See if I can get it there. So I'm going to say 0 has exactly 0 has more than one y. This one's not a function. 0 has more than one y value. Okay. 17. First, we have to identify the depend statement, dependent and independent variables. It's not too bad because we know that the dependent variable is always on the y-axis and the independent variable is always down here on the x-axis. So our depend statement is going to be that cost depends on size. Cost depends on size. The dependent is the cost, and the independent is the size. Now the only last question we have here is the function. Is it a function? Can we cross this more than once? Actually, yes. Right here is a good instance, a 3. So it is not because 3 has more than one y value. 3 has more than one y value. Last, depends. So we have got that light bulbs is our dependent. So our light bulbs depends on the year, because years are independent. Depends on the year. Okay, so our dependent is light bulbs. Light bulbs are a dependent variable. And the independent is the year. The only question is it a function? So the question, can we cross this twice with a vertical line? Not here, not here, not here. We only hit it once everywhere, so this one is in fact a function because every x every year has one amount of light bulbs sold. Okay, well, that brings me to the end of these notes. Now for my random math fact. There is a mathematician out there. He actually is really big in the field that I wrote my thesis in when I got my master's degree. His name is Paul Montel. There's Paul Montel. A couple of cool things about the guy. One, he looks great in a suit. If you look at any old pictures of him, but also he was born about 100 years before me. But we have the same birthday, other than the year. We're born the same day in the year. And if you notice, this is just Melton rearranged. That's spooky. Put it right there. L right there. T, the O, and the N. Our names are permutations of each other. So, there's our interesting math fact. Tune in next time for evaluating functions.